I'm very happy to introduce Professor S. Keshav today to talk to us. Keshav has at various times been an academic, an industrial researcher, and a Silicon Valley entrepreneur. And now he's moved back to academia at the University of Waterloo in Canada, where he's working on, among other things, the problem of getting low-cost, reliable internet access to India, and has come up with a novel way of doing so.
Thank you. I should add that this work is joint work with Aditeshwar Seth, who's my PhD student. And so all the good ideas belong to him, and if there's something doesn't look quite right, that's my contribution. So that's where we are. So let me start off by saying, what is a kiosk? A kiosk is, think of two things, technology and a person. Technology because you want to do some communication or something special, and a human operator because the people who are using this aren't quite up to using it themselves. Maybe they're illiterate. Okay, so you need a human operator. Today, kiosks provide a variety of government to citizen services, and I have a list over here which you can read. We are working with a partner called eGov Services, who are based out of South India, and they provide 200 different services, including actually mutual funds, crop insurance, railway reservations, and so on and so forth. And I'll talk a little bit more about how the technology works, but this is actually out there. They're actually well-established means of delivering technology to large countries. The public call offices, or what in India is called STD, ISD offices, there are about 150,000 of them right now, and they're all profitable. And they all actually support one entrepreneur. So you have 150,000 people who are making a living out of this. And based on the success of this particular model, the Ministry of Information Technology in India is proposing to set up 100,000 kiosks over the next 2 years. And there are several people who are trying to bid for this opportunity. So this is actually something which is happening, and the bids are going out. And what we're trying to do in this research is to actually make these kiosks useful. So to make a kiosk useful, it has to be connected. Okay? If it's not connected, it's not doing any work for you. And the three options that are out there for connectivity are dial-up, VSAT, a very small aperture terminal, and long-range Wi-Fi. So dial-up is, your typical phone modem. You're going at between 8 and 28 kilobits per second. And the problem with this is that you're going over a wire. And in a hot, dusty environment where people are digging all the time because they're building buildings and roads, you have outages. And these outages take fairly long times to fix, typically 3 to 4 days. So if a kiosk is down for 3 days and somebody comes in and says, I want my birth certificate or do some kind of financial transaction, you're going to turn people off. And in fact, project after project in India and other countries, the kiosks have died out because people go to the kiosk, it's shut down because it doesn't work. So part of what I'm trying to do here is to address that problem and say, how can we make kiosks that are low cost and reliable? And we'll talk about that both from the operating system perspective and the communication perspective. The VSAT, very small aperture terminals, are popular. These are like pizza-sized dishes, which you can put on the roof. The problem is that upfront cost is fairly high, plus there's a monthly rental fee, and the monthly rental fee is also high. So if people who do this kind of thing with VSATs end up making a loss, they're not able to sustain themselves on the kind of transaction fees that you're extracting, which is roughly between 5 and 15 cents a transaction. So you can't really do that. There's not enough money to pay for the VSAT. And spare parts are hard to get. And long-range Wi-Fi is, a couple of people are trying to do this. There's work out of Berkeley, work out of IIT Kanpur, and so on, to take 802.11b and make it very long-range and make it low-cost. It's experimental. The upfront expense is not in the Wi-Fi card, as it turns out, but in the tower cost. Trees are roughly 16 meters in most parts of India, 50 feet. And you need 18-meter towers, and 18-meter towers are way more expensive than 15-meter towers, which are way more expensive than 10-meter towers. So the cost goes up exponentially. So the big cost is in the towers. So tower costs roughly $1,000, okay, which is essentially unaffordable for the kinds of deployments thinking about. 100,000 kiosks at $1,000 is $100 million, right? So what can you do? And this is something called mechanical backhaul. And the idea is not mine. The idea is due to a company called a project called DarkNet, which is done out of MIT Media Lab about 3 years ago. And as you can see on the right-hand side, they have this bus, and they actually put a Wi-Fi access point on the bus and a small device which has storage. And when I don't know if I can get my mouse here. Okay. On the left-hand side, we have this. We have these kiosks in the villages, and in each kiosk, you have a Wi-Fi box. And what it's doing is it gives it to the bus, and the bus actually carries it to the city, and it goes off into the city, and it goes round and round, very much like what a postman would do. And the term mechanical backhaul is due to Arno Penzias, who said, oh, this is just doing backhaul, but you're doing it mechanically. So I love the term, and I stole it. So both the idea and the term are stolen, okay, which is in the normal research practice. So what are you going to do? So this gives you the intuition of what we're trying to do. And what I'm going to show you in the next few slides is that while it sounds simple, here, you just put a bus and access point. In fact, you have to re-examine the very foundations of networking. Things like naming, addressing, routing, locationing, all of these things are completely changed. And so I'll talk about an architecture, and I'll tell you about the open problems and our implementation. And just to give you a sneak preview, we're actually going to deploy 2 of these in May in South India. So this is not just talk, we're actually going off and doing this. So what are the goals? In academic research, it's very normal to come up with random assumptions and goals, okay? But you're trying to build something for the real world, you have to make sure the goals match what's out there, otherwise you're building the wrong thing. So these are the goals we have. The first one is low cost. Low cost because you want to have mass scale. So we want to have less than $250 per kiosk upfront and less than $50 a month operational cost. And this $250 includes the PC or the machine that's providing the services, as well as all networking. Everything has to be in the $250. So it's fairly stringent. We want it to be reliable because, as I said earlier, if it's unreliable, people just get turned off. They don't want to use it anymore. We want to allow user mobility because it turns out social studies have shown that villagers actually move in about a 15-kilometer radius. And it's not as surprising as you would think because they're going to the market towns to sell their produce. They're visiting relatives in other villages. There may be peddlers or small-time traders who are picking up goods from other towns and bringing them to villages and so on. Mobility is necessary so that the villagers or the people using this are able to use the kiosk that is closest to them instead of being tied to a particular home kiosk. Okay, they don't have to go, they can go anywhere and pick up stuff. We want to have data privacy to allow banking transactions, maybe medical records, financial transactions of any sort. So we need privacy in the specific sense of authentication and message privacy. We want to be able to use existing internet services because there's a lot of stuff out there. People want to use Google no matter where they are. So we want to, but Google or the servers in Google are not aware of disconnections because we don't have a connection all the time. So how do you do that? We want to exploit every possible connectivity option that we have. Some kiosks will have dial-up, some will have dial-up and long-range Wi-Fi, some will have VSAT. Whatever is there, we want to use it. And so we have to have an architecture that allows you to specify, this is an urgent message, send it on a cell phone. This is a message that can wait, send it on your Wi-Fi whenever the bus comes by, and so on and so forth. And finally, we want to support 2 classes of users, kiosk users who are going to a kiosk and using something there, and people who have their own device. It could be healthcare workers or government workers who have a PDA and so on, and they want to use it. So I'm spending a lot of time on the goals because, as you can see, if I don't have the right goals, then I'm going to design the wrong thing. So if you have any questions about this, I'll answer that now. It makes sense. Okay, so why is it hard, right? I mean, if I have these goals, what makes it difficult? The first thing is that we don't really have a connection end-to-end. If somebody is on a PC, on the kiosk, and they want to access email server, say Hotmail, or they want to do some web query, both ends of a so-called connection are not simultaneously present. So you can't really run TCP end-to-end because guess what? All you have is TCP to the bus, and then an hour or 2 later, you have TCP from the bus to whatever is the back end, but you don't have the same thing end-to-end. So you can't do things like TCP window flow control end-to-end. You only have hop by hop, right? That fundamentally changes the character of what you can do. So you can't use standard TCP. You can't use DNS because there isn't a DNS server you can talk to. All you can talk to is a bus. You can't use SSL because SSL has a 3-way handshake, right? It says, here's my nonce. You can't use that because there's no, it's all hop by hop in some sense. So that's one change in mindset. The second thing is that there's a bunch of technologies that are out there which have been using, which are mobile IP, HIP, the alphabet soup of things, which all are using, which deal with mobility, and some of them deal with disconnection. But they typically assume you're mostly connected and rarely disconnected, or you switch. If you think of TCP migrate, for example, if you're aware of that, You're saying, well, my IP address keeps changing, but I'm connected all the time. And you just kind of flip the IP addresses using a handshake, using your public key or something like that. But here we're in the opposite regime. We're mostly disconnected and rarely get connections. You have transient upload as the bus goes past, and then you have transient and another bus goes past. And then finally, we have these issues of low cost and reliability, which are very stringent assumptions. And these change the design. And without going into too much detail, we did look at all the existing work and couldn't use them. So what is it we can use? What are the building blocks, the Lego blocks, if you will, that you can put together to get what we want? And one is we can use storage. Storage is very cheap. $2 a gigabyte, you can get maybe $1 a gigabyte, maybe less if you're buying it in bulk. Wireless networks are everywhere, and both the cellular kind of wireless networks, Wi-Fi, these cards are cheap and ubiquitous. And then there's this new technology which has come out in the last few years called delay-tolerant networking. It came out of the Interplanetary Space Research Group out of JPL, but then there's been a considerable amount of work being done out of Intel Research Berkeley by Kevin Fall and others. In a nutshell, what it has is an overlay network on top of the internet. So what you're talking about is hop by hop, and each hop is TCP/IP for the most part. And we send messages which look like which are called bundles, which go over potentially disconnected links. So which is exactly like the kiosk to bus and the bus to the next hop. And think of it like email. Right? Email doesn't require you to be present. Both ends don't need to be present. You just dump it in your mail server. It makes its way somehow to the destination mail server, and then somebody picks it up. And that's what DTN does, except that you can do better routing, and I'll talk about routing in a bit. And finally, DTN allows you to have extensible naming, addressing, and routing based, naming and addressing based on URIs. So everything is a URI, and we do name-based forwarding. And so these characteristics of DTN are very well matched to the kind of things that we have. However, DTN does not address things like mobility, does not address issues like security and routing. So we actually have extended DTN to take care of those issues. So that was the big picture. What are the goals and the principles and the techniques? And now I'm going to kind of dive right into the architecture. So this is what it looks like. And here I'm going to kind of wave my hands because I don't have a pointer. I'm not supposed to use a pointer. And I don't have a mouse either, I guess. All right. So what we have on the left over here is this bus route A. And the bus route A, can you think of as a regular bus route where you have a guy in a kiosk who's a regular user. And the bus picks up the data and goes to an internet gateway. So the bus goes round and round, picks up data from here, and then opportunistically, and then drops it off at that gateway, which is the brick wall over there. And there it enters the internet. And the upload is typically through a DSL at about 100, 200 kilobits per second. So it's not super fast, but it's OK. This over here represents a very interesting case where the bus is dropping stuff off at this intermediate kiosk, and then you have another 2 kiosks which are simply connected through this intermediate bus kiosk over here. So the kiosk is actually acting as a store and forward router. Okay? And in the third case over here, bus route D is actually not talking to a kiosk. It's talking to somebody who's at home. And they're picking up stuff along from that person's house as they go past. So all of these are typical use cases, and we would like to support all 3 of them. We also have users who are kind of going from one kiosk to another, and that's represented on the bottom over there. So that's the architecture. So what does it look like in a kiosk? And what we have is a design that we want to make work in very limited circumstances. So what we do is we give the kiosk controller, the entrepreneurs running the kiosk, what we call a kiosk controller, which is this Socrates box. So those of you who've seen it, it's about 8 inches, about an inch thick. It has no fan. It has a low-power CPU and a couple of PC card slots. And it's headless, keyboardless, no video out. It takes only 7 watts. So we can take a 10-watt solar panel, stick it on the roof, put it on a lead-acid cell, a gel cell, and power that for 5-6 hours based on that. And what it does is that it has inside it a RAID 1 disk. It's a mirrored disk, and provides netboot and a file system and a WLAN access. So what the entrepreneur does is to go buy a junk PC, a second-hand PC, costs about $100, sticks it into this box and hits reboot, and it comes up clean. Comes up running, the box is running Debian Linux. The PC comes up running Linux using terminal services. It's actually hacked up terminal services. First thing to contrast this is with one laptop per child project. As you know, MIT is trying to do this thing with this one laptop every child is given, And the difference contrast is immediate. We have one recycled PC per village versus one laptop per child, so the cost targets are about a factor of 100 away. We're 100 times cheaper right off the bat. The second thing is one laptop per child will get dust on it and it'll break down. I mean, it's going to happen, right? Somebody leaves it in the sun for 5 minutes, it's going to fry. Where are you going to get spare parts from, right? Whereas here, spare parts for PCs are, they are in fact everywhere because there are about 700 million of them and people just have these things. And getting recycled PCs is kind of easy. How many of you have an old PC in your garage? Okay, chances are pretty good. If I ask for donations, I'll have 20 in 5 minutes, right? My lab is full of recycled PCs. I just ask once, and people are throwing it at me. It's easy to get these things. So they will run, for sure, they will run pirated Windows. Okay, that's what's going to run on these PCs. They will run on its software, which is not quite the right thing to run. Okay, and it's going to have viruses, adware, spyware, malware, whatever. It's going to have all sorts of junk in it, and that's okay. What you do is you put in the Ethernet cable and press reboot, and it boots from the net, and it's not going to use your disk. It's just going to use RAM disk, and it's going to be clean. So that's the way we designed it, and this is all working. So we can take any old PC. We don't care what's on the disk. In fact, you can junk the disk and just boot off the Socrates, and you're okay. And so we have, as I said, spent some time thinking about what are the environmental conditions under which this is going to be used. Inside ferries or the buses, we call them ferries, data ferries, and gateways, same kind of thing. We have a box with some RAID on it. Here is not, it looks like from a networking perspective, is a graph. What I've shown over here on the top is this cloud, which is the legacy server, whatever server, and it goes to a proxy. We have a proxy to hide disconnections from the rest of the world. So from the perspective of legacy server, all you have is a proxy, and I'll go deeper into what's inside the proxy in just a minute. These I1, I2, I3, and so on are internet gateways, and these dashed lines represent slow links. Slow meaning about 100 kilobit per second, as opposed to the Wi-Fi links, which are 10 to 50 megabit per second, considerably faster. These rings called B1, B2, B3 are the bus routes. And this actually opens up a very funny question, which is how do you draw a network where the nodes are moving? Okay. When you talk about a graph, a network graph, you draw a graph and you expect everything to stay where it is. But here I have a node which is going all over the place. And in fact, I don't think this is the right way to do it either, okay? Because I can talk about that offline further, but representing statically the bus routes turns out to be very problematic when you're trying to do any kind of link edge, link weight-based routing topologies or routing metrics, OSPF or something like that, because depending on different points in time, the cost of the links changes. So time varying cost per link. Failure probabilities also change, so it gets messy, but for the moment, this is a first order approximation. It seems to work. And as you can see, we have user 2 over here going from one kiosk to the other. Kiosk 1 is on 2 bus routes and so on. And one can imagine constructing shortest paths on a graph such as this. And in fact, it does do the right thing, though there are some problems I'll talk about later. So this is just to give you an idea of how the whole thing models as a graph. So this is the protocol architecture, and bear with me, it's not as horrible as it looks. On the left, we have the kiosk, and I'm showing an SMTP example. So on this line over here is your standard SMTP, hello, from, to, data, quit, right? Standard stuff. What's happening is the kiosk controller is running SMTD, and it's running SMTP daemon, essentially saying, I'm the mail server, and it fakes Hotmail, whatever, Gmail. It says, I am whoever you want me to be, and gets all the data. And what it does is it puts them into this protocol called OCMP, which is our own protocol, called Opportunistic Connection Management Protocol. And OCMP essentially grabs the data, puts it into persistent storage on a MySQL database. And the reason is because the Socrates bus is going to go down. We have 5 hours of power, but it may be a cloudy day, right? So when it comes back up, it's just FSCK, the equivalent of that, and we know what bundles are out there. So we're power fault tolerant. And then we have this thing called a DTN, a bundle protocol agent, which essentially grabs the bundles, sends it to a network of routers using DTN routing, and off it appears into the proxy. And in the proxy, you have this application ID that says, this is email application. And we have a plugin on the other side, which gets the data and sends it to the regular email server using SMTP, which is over here. So essentially what we've done is taken a normal TCP IP connection and put it into these bundles or messages and replace the whole thing under the covers so that neither the client nor the server needs to know the difference. Okay, so any questions about this so far? Okay, so now the talk gets hairier. This is the easy part. All right, so we're going to talk about naming and addressing, and let's see. Okay, we have about half an hour. All right, so we use names for everything. Ferries, kiosks, gateways all have a name, and for us a name is just a string, any string you want. It could be your name and address, it could be your phone number, it could be your email address, it doesn't matter. For uniformity, we just hash it and you get a 20-byte string which you use for forwarding. So it's a name-based system where all the forwarding is done on names. Clearly, you see right away you don't need DNS because all you're going to do is to simply hash your name and you get your address and off you go. We call this a GUID, Globally Unique ID. Now, we have this complication of disconnection, right? Disconnection says you can send it to somebody, but they're not there. They turned off the PDA. Or you send it to kiosk, and the kiosk is down because there is no power available right now. So what we do is we have this notion of a custodian, and a custodian is somebody who's usually supposed to be on all the time, okay? It's exactly like your name at mail server. You're not there, but your mail server is there for you. So that's your custodian. So we have this notion of a custodian. And they said that everything has a GUID, so custodian is a GUID. And so the full name of somebody is going to be this custodian GUID, user GUID. Just like name at mail server, that's my GUID, is custodian GUID. In the same way, we have this tuple. And what we're going to do, what the sender is going to do is to send it to the custodian's GUID somehow. And then after that, the custodian will figure out how to send it to the user. Okay, so that's how you deal with disconnection. And the custodian also acts as an anchor point, which is shown in this picture over here. So for the regular kiosk user, the custodian is right here because that's where you're going to pick it up from. But a mobile user will pick a custodian over here, which is the closest point under which you're moving in terms of the subtree. So wherever you are, just pick it up from the custodian. So when you go to this village, you say, OK, I'm picking up from here. When you're in that village, you pick up from there. And everything is cached there for you or staged there for you to pick up later. And in the case of bus route D, the custodian actually is the bus, because the bus is the point which is going to give you your stuff. So the notion of custody is fairly nice. It allows us to deal with disconnection properly. Okay? Now, I've not talked about mobility yet. I'm just talking about disconnection. However, we have to deal with mobility. And what mobility means is that your custodian can change, right? Because you go to a different place and your custodian changes. So we need to somehow tell senders that I'm at a different custodian. And how do you do that? You use an old trick which cell phones have been using for 20 years, which is to have something called a home location register, which says, if you want to reach me, I'm available and so location. And what we mean by location here is the custodian's location, because that's what's going to get to me. So what we do is that we have this home location register, which is this big lookup table in the internet. Think of it as a distributed hash table if you want. And every user says, my GUID is X and my custodian is Y. So if anybody wants to reach me, tell them to send it to Y. Okay, and we put that in the home location register. Now the sender may not know why, because the sender may be disconnected also. The sender is some other village. So what we do is that we have a special custodian name called unbound, which says, I don't know who the receiver's custodian is. I'm just going to put the unbound. And whenever the bundle gets to somebody on the internet, then that person can bind it at that point in time to the right custodian. So you're kind of sending this message with the GUID of the destination, but with no custodian name, but then halfway through it figures out where it's really supposed to go. An analogy that might help is to send IP packets with names in the header. And when it gets too close to DNS, it resolves it to an IP address, sticks the IP address in, and then you know where to go. Right? We're doing the same kind of thing, except we're doing it name-to-name translation, okay? Unbound to a name translation. So how do you set it up? Well, that's done through signaling. It's a standard control plane. In the cell phone, when you turn on your phone, a register message is sent to your what's called a visitor location register. It says, so-and-so cell phone is in so-and-so tower area. Same way over here, we send a register message which goes, quote-unquote, towards the internet. And the way you do towards is by configuring every router with a default route that says, this is my default route to go to the internet. This is what you do today. So by just setting one configuration parameter in every router, every DTN router, you know exactly how to get to the internet. And the register message flows up to the internet, and then you update the home location register saying this is the custodian. Right? So that's the solution in a nutshell. There are quite a few race conditions, and there's a paper I can share with you which has all the solutions to race conditions, which are a little bit tricky. Okay, so that gives you kind of a flavor of the naming and addressing. And so to summarize, we have to have custodians to deal with disconnection. Users have names. Names are any string that you want. Forwarding is done based on the names. How do you do forwarding based on names? That's routing. Okay, and that's what I'm going to talk about next. So we've just assumed that magically the sender has a GUID and it magically reaches the destination, but this is actually pretty hard to do. And I'm going to tell you 3 solutions, and then when I show you the third solution, I'll tell you why it's hard. So the first one is just flooding, which is just dumb. Give everything to everybody. And it actually works, right, by definition. It also finds the shortest path because it finds all paths. But it's not something you really want to do. But for very small deployments, you have just a couple of buses and 5, 10 kiosks. Why not? Just send it to everybody. The second choice is what we call reverse path forwarding. And this is it's easy to understand, but conceptually it's tricky. So let me show you what we're doing over here. So imagine the user U5 on the far right corner who wants to, who I said is registering with the HLR, right? That's what you do when you change a location or you go to a new place or you come up for the first time. So U5 is going to send this red message along this particular default route all the way to the internet saying, hey, register me. Now, what we do is very simple. Let's say you look at kiosk K3. When K3 gets a message from bus 3 saying U5 is registering, it says, oh, U5 is registering through you. Therefore, if I want to send to U5, I should just give it to you. I just swap the route back. This is a very old trick that dates back to the 60s, I believe 67 or something like that. It's called reverse path forwarding. It says, if I got something on this port, I must be able to reach you on that port. And you just do that recursively and you get to the top. And so the registration, which is a location update, is actually co-opted to do routing table as well. So you're doing routing and locationing at the same time. It sounds very clever, but it has a fatal flaw, which is that it's a single spanning tree, which means it's susceptible to failure. So in this case, for example, bus 2 goes through Internet Gateway I2 and I3, but it has decided that the default route is I3. So if I3 goes down, though I2 is a perfectly reasonable way to go, you can't use it, right? Because that's not the default route. Okay, so there are simple hacks to get around that, but generally speaking, because you're constructing a single spanning tree, you get efficiency because it's a single copy, not multiple copy, but it's fragile. And so the one hack again, or one way to get around that is to have a soft state. Every half hour, you send a new register message. So if you're down for half an hour. And that's exactly what we're doing on our implementation today. But it's not very satisfying because this is not very good. What you really should be doing is link state routing. Okay, this is the kind of the holy grail, which is to represent each link in a link state packet as you do in OSPF and then flood it. So that everybody constructs their own topology, constructs shortest routes, and so on. The 2 problems over here. One is that I don't know how to draw a topology for a bus. I mean, that ring I showed you is a first approximation, but it's not very good. Because imagine that there's a bus and there's a user who's just picking up data from the bus as it goes past anywhere along its route, How do you represent that, right? What is the link metric that goes from the bus to the user? It depends where the user was, okay? And in fact, the routing policy you should have depends on where the user was. If you catch a bus just as it's setting out from the bus depot, which is the internet gateway, then the best routing policy is for the bus to give it to another bus which is going back towards the bus depot on the opposite direction, across the street, so that it goes back to the depot. However, if you catch the bus towards the end of its duty cycle, then it should just keep it, right? So the bus has to make this kind of decision, and we would like to make the decision using standard OSPF and standard link metrics, but I don't know how to draw a graph. So this is really kind of funny because I've been studying networks for nearly 20 years, and I've never run into a situation where I don't know how to draw a graph. Well, anyway, maybe somebody can help me here. The other thing is that determining a link metric is hard because, as I mentioned to you, the uplink is a DSL or something like that. That I3 uplink is a DSL. So that's about a gigabyte a day, ballpark, gigabyte a day. The buses carry about 40 gigabytes in the disk. So if you dump the whole contents of a bus, you have 40 days of queuing at one router. Okay, sounds crazy, but it's possible, right? So you want to be very sure of which particular gateway you're choosing. However, the link metric, in this case will be the queue length, changes before you get there. So the bus may decide when it gets here, it says, oh, I3 is heavily loaded, I2 is lightly loaded, so I'm going to send on I2. But by the time it gets there, somebody else may have dumped stuff onto I2. So the metric has changed on you because the time scale is ours, right? And some other bus, some other opportunistic connection has dumped more stuff in it. So managing these link costs becomes quite important. And pathological cases are very easy to construct, where you have ping-pong routes or you have very large delays and so on. The solution that we have in mind is to use cell phones and use them as a serial modem and hook them up to our Socrates boxes and send at 8 kilobit per second, which is the GPRS rate, routing updates. So because the real underlying problem is that the time scale at which your routing links are changing is the time scale of forwarding. Okay, another way of putting it is, when you do TCP flow control today, you do window up and window down, your additive increase, multiplicative decrease, but the path is fixed, the route is fixed. It's not changing on you, because routes are changing on the order of 5 minutes, and the TCP is changing on the order of 100 milliseconds. Here, the rate at which data arrives and the rate at which the links or routing metrics are being updated are in the same time scale, which is why you have this problem of time scale coupling. We need to decouple it, and the way to decouple it, as I said, is to use cell phones, and that's one way of looking at it. But load-sensitive routing, which is really what you have to do when you have open-loop flow control. We can't do closed-loop flow control because the round-trip time propagation delays are in the order of days. So you have to do open-loop. So open-loop flow control with load-sensitive routing is a known hard problem. And for those of you who remember the old ARPANET metric, the load-sensitive queuing metric, will recall that it had horrible oscillation problems, and we want to avoid that. And so we need to figure it out. We don't have a solution yet, but we have some good clues, and this is our current work. Okay, so how about security? Kind of switching gears here. Why do we need security? Well, as I mentioned earlier, you want privacy and authentication for banking, secure email, bill payment, reservations, and so on. Obviously, you want non-reputability and things like that. What we've looked at is why not use PKI, mainly because I don't know the public keys of everybody, right? I mean, I have to, if I go ask a PKI, give me the public key of so-and-so, well, it's hard to find. You could use certificates, but then you have some revocation problems because you have to tell everybody revoking is a problem. So what we're looking at is a different solution which is based on identity-based cryptography. This is something that came out of Stanford about 5 years ago. And the idea is very simple. Your public key is your ID. Remember, your ID is just a hash of your name. So if your name is a@b.com or user@provider.com, then I just hash it, that's your public key. Now, if I know your public key, then I must introduce a secret to create the private key, because there's an algorithmic way to go from public to private. Everybody knows your private key as well. So it has to be an additional secret, and that additional secret is injected by something called the private key generator. So this is sort of how it works. You say, you go to a kiosk and say, I want to sign up. I want to sign up as a user. And then the kiosk guy says, OK, your username is so-and-so at so-and-so provider. And by the way, that's also, you hash it. That's your public key. And that's also your address. All three are the same. OK? And then the private key has to be given to you by private key generator. And we have a protocol, which I'll probably skip in the interest of time, which allows the private key generator to give you your private key over a disconnected network. Okay. So the nice thing is that if I know somebody's name or their phone number, I can send them a secure message. I've established a secure channel with them with the property that the private key generator can spy on everybody, which is a bug or a feature depending on which country you live in. Okay. In this country, it's a feature. In Canada, it's a bug. Okay. So given this thing, you can actually communicate anybody you want to. Because you just need to know, say, bank 1 at Main Street, wherever. You take that whole string, hash it, and as long as everybody agrees that's the bank's name, you actually have secure channel to them, which is really great. And so you're standing by the roadside and you want to send a secure message to anybody. You don't need DNS. You don't need PKI. Right? All you need is to know how to hash, which is easy. There are some schemes we come up with on how to give a disconnected user a private key, and there are some interesting corner cases to worry about because the kiosk guy is not to be trusted. He's somebody who's just a random person who wants to make money. So how do you make sure that guy isn't using the people's bank accounts to make unauthorized withdrawals? So we have a scheme that uses essentially shrink-wrapped cellophane wrappers around the SIM card-like things to do that. We have to worry about revocation. If you have a smart card or a RFID which represents your key and you lose it, you don't want people to be able to use it. And so we have some schemes for revocation, and we also have schemes for mutual authentication where a user and a kiosk and a bus can authenticate each other. So you're standing by the street, a bus goes past, you can be sure that it's a valid bus, and the bus can be sure it's a valid user, and they can audit you, and they can also set up a trail of usage they can bill you. So I'm going to skip those things and kind of go on to the next part, which is application support. I had given you a preview of the application support earlier where I said that when you have the email, you have this server pretending to be the mail server, and it's using something called opportunistic connection management protocol. So I'm going to talk now for native applications, supporting native applications, or supporting applications which are the server side, which are pretending to be applications, native applications. So we want to have a simple API to use it. We want to allow session persistence. It means that the client and the server has some session going, be a file upload session, and the session persists despite many buses going past. So each bus carries a part of the session, and that's okay. It's all put together the right way. We want to be able to choose which network to use, right? If you say, I want to use a cell phone link, even though it's expensive because it's high priority, I want to be able to choose that. And finally, I want to allow legacy servers. And the solution is this thing, OCMP, and it's a Java-based application. So you can run it on smartphones, and you can also run it on kiosk controllers. And we run it actually on a bunch of different platforms. The one nice idea is to hide disconnections under a directory API. And the idea is that you drop something in a directory and it magically appears in some other directory somewhere else. This is actually, I was motivated by the Plan 9 file system, which allowed you to use directories for mapping FTP. So the FTP map stuff, which I think, Dave, maybe you did that way back when in Bell Labs. They say, oh, that was a cool thing. So we're using the same thing over here. You have each application is associated with the upload and download directory and has a status and a config file. So the config file says, what are my parameters, username, password, and each application can simply drop stuff into the upload directory, and it magically appears in the upload directory in the corresponding server on the proxy, and then the proxy plugin on the other side knows what to do. So it makes it very easy to write apps, and as I'll show you in a minute, we've done about 6 apps already, and I can get a student who has no exposure to this to write an app in about 2 hours training. Okay? All they need to do is grab a file, drop it in a directory, and then forget about it. So most of the work actually is writing GUIs. We use proxies, and we have this ability to relocate open connections, which is not particularly relevant to this project, but we're using it in a different project. So this is now the complex slide, and I'm going to spend maybe 5 minutes walking you through it, because it's kind of cool. At the top left, I have the application, and just look at the middle line which says Directory Watcher Plugin. So what the app is doing is just dropping stuff into a directory and then forgets about it. The nice thing about this is it encourages people to have non-chatty protocols. You don't want to have request response type things going over directories, because you drop in a directory, you don't know when the response is going to come. So it forces people to do the right thing. The Directory Watcher plugin is part of our OCMP implementation. It simply watches change times. And when it sees something over there, then it segments it into bundles and puts it into persistent storage, into a MySQL database or equivalent. It's just, you don't really care what database you use. The reason is because this thing can die, right? When you come back up again, you just recover, as I mentioned earlier. Below it, we have this thing called a connection pool. And what a connection pool is a bunch of sockets. Okay, each socket is bound to a particular NIC, a dial-up NIC or a GPRS NIC, or in this case, a bundle protocol agent NIC. So we have a pool of worker bees, and I can say, here, send this bundle, and it just goes and sends the bundle. So all the applications share a single connection pool. So we really only have one end-to-end connection. And as those of you recall from HTTP 1.1, having persistence TCP is a good idea when you're talking about dial-ups. You don't have to go through a slow start each time. So the connection objects are sitting over there, and what we have is the ability for the, when you choose to send a bundle, we do an up call into the application saying, look, I'm about to send this bundle, where do you want me to send it to? And that allows you to have very fine-grained selection policies, okay? Now, what the policies actually are is still current work, but we have the mechanism to choose exactly which NIC you want to send it to. And when it gets into that, it goes, in our case, the BPA, the bundle protocol agent, is running on the kiosk controller and also running on the bus. So it gets the bundle and puts it into local persistent store, the disk, drives it over, and it comes to the internet gateway with also running a bundle protocol agent, and off it goes over the internet, over the DSL line, to the proxy. And the proxy gets the bundles, reassembles them, and basically calls the application plugin. So what OCMP is doing is the ability to provide plugins to do segmentation reassembly. It does proxy to client session persistence, and it provides the selection, NIC selection choices. So these are all the things that OCMP is doing, and you can think of it as essentially application support for DTN. Okay, this is implemented, works. Oh, great, that's the next slide. So we've implemented all of our stuff as an extension to the DTNR, the DTN Research Group implementation, which is a C++ implementation. So we've added all the application support to it. We also added the reverse path forwarding support to it. The application support is on Java. It runs on PDAs, on Cream, on any standard Pocket PC 2003. And the home location register that I mentioned to you is actually using OpenDHT from Intel Research at Berkeley. We've made some simplifications for the first implementation. The first is that we kind of restricted custodians to be internet gateways. So all custodians, internet gateways are also custodians. We're using reverse path forwarding routing. We're not doing load-sensitive routing. We haven't implemented the cell phone-based control plane, though we'd like to. And we're not doing any data replication. We could easily do tornado codes over UDP instead of TCP, but there are some funny interactions between data replication and flow control or open loop flow control that we haven't quite figured out. So we aren't doing that right now. But we have made these following changes. We have a separate control plane. So we have an app called the control plane app, which makes it very easy to say this control plane app will always use the cell phone. So this data plane control plane separation is something that I really believe in, and so we've done that over here. We have extended the DTN namespace, the URI namespace, as I mentioned, to have the tuples, the custodian ID and the user ID. One problem is when a user walks up to a kiosk, they don't know anything about 20-byte strings and all this other stuff, right? What we, in fact, give them is Unix IDs, just standard UIDs, and you say your Unix ID corresponds to this 20-byte string. So the end user is never actually exposed to these UIDs. They're just getting standard logins and passwords on the Linux box, okay? And so that allows us to keep track of the file system very cleanly. And we have a file called HCID map that maps from a Unix ID to a GUID. And as I mentioned earlier, all the recycled PCs just mount the root file system from the Socrates box. And so they inherit the same UID architecture. So we don't have to worry about YP password. We just get one UID and everybody's happy from there. We just use webmin to create UIDs. And finally, the home location register is implemented using OpenDHT. In the original DTN implementation, there's no mobility support, so we had to add that in. So all of this stuff is actually done and working. OCMP is implemented in Java. We're running it on Linux, Windows XP, WinCE, and a student at IIT Delhi working with us has ported it to .NET Compact, so it runs, or should run, on the .NET Windows mobile platform whenever we get our hands on it. The code is open source. It's being used already by UC Davis, a student UC Davis for RSS newsreader. Sprint is using it for HTTP, and IIT Delhi is using it for XMPP, Jabber or Gtalk. These are the applications we have running right now. We have a mobile blog, and this was the first thing that started. The whole idea was to take a photograph or enter some text, put it on your PDA, and then walk past the Starbucks, right? You can do the same thing over here. You can walk past the kiosk. So you're a journalist or you're some random person who wants to upload things. You can just go past the kiosk, and it'll actually sync up with the Socrates box, put it in your user directory. The bus will come and take it away. I was talking to a student yesterday at Berkeley about the situation happening in Rwanda about malaria control. They don't know who has malaria in which district. So they have these shipments of malaria control drugs which come in and just randomly send it to random districts because they have no clue where it's going. They have no communication infrastructure in place. So when you say somebody is sending these things up, one thing we're trying to do, and I hope it will work out, is to give these guys in Rwanda a Socrates-based thing in their car that they drive to the district with, and the OCMP would run on their cell phone. And you could actually do a survey and say, what is the incidence of malaria in this district, and have it collated and be uploaded and go to the central government, which actually knows where to send malaria medicine. Right now, they're just doing whatever they feel like doing. It's pretty horrendous. We're looking at Jabber, not because you could do instant messaging with 1 day delay. You know, it's sort of, is it instant messaging, or what is it? But Jabber is a nice app because it has 3 modes. You can do file transfer, you can do email, and you can do instant messaging. So you get all the 3 kinds of things. And you can actually do instant messaging on top of dial-up, right? So you want to actually separate out within the app that these bundles go on dial-up, those bundles go on Wi-Fi, those bundles go on GPRS or whatever. So we can actually think about doing those things. So Jabber is a nice test case. We have HTTP GET for obvious reasons. We're working on email. And I'll take a minute because this is kind of interesting. We're using Thunderbird, and we are internationalizing, just doing the internationalization extensions. And this gentleman showed up at my office 2 weeks ago saying, I can do any language you want using 6 keys. And he's figured out a way to use 6 keys to enter 12 different languages. He can do 5 Indian languages. He can do Chinese, Korean, Bengali, Gujarati, Hindi, and Inuktitut, which is what the Inuit speak in northern Canada. And he does it with 6 keys. And he just saw my website and showed up. I said, can you do Telugu? Because the deployment is going to be in Andhra Pradesh. And he said, give me 2 days. He comes back 2 days later, and he has Telugu. He doesn't read or write the language, but he's a speech pathologist, and he knows how to do these things. And he taught himself basic programming, Visual Basic or whatever, and he's writing the stuff. So we're going to have English keyboard with 6 keys with stickers on them, which will be used to enter Telugu. And we'll provide Telugu email in our deployment. So this is kind of nice. So if you're interested, send me mail. I'll send you. He has a website with a video of how he does these kinds of things. Flickr is upload is underway. Flickr is a great way, and if you're looking for photographs of where is the water collecting, for malaria prevention programs, you can take photographs and actually upload them using this. So Flickr is a nice way to do that. So as I mentioned, the DTN2 extensions are done, OCMP is done, the kiosk controller is ready to go, and if anybody is interested, we're writing up a tech note on how to make your Socrates box work this way so you can just replicate this. Security is being developed standalone. We need to integrate that. It's going to happen in the next couple of months. And we'll do our first deployment in 2 villages in Andhra Pradesh in May. So we're going to go off and do this. Conclusions. Okay, so what were the goals? We wanted low cost. So the Socrates box costs about $200, give or take, depending on what you put in it. The recycled PCs were $100. So we're roughly in the $250 ballpark, right? Which is not bad because a village of 500 users, you're talking 50 cents a person, which is okay because this includes communication plus computing. Reliability, I don't think we got there because we need to do data replication and we got stuck with routing. So once you get the routing figured out and the flow control figured out, we can do reliability. But for now, I'm not too happy with it. We allow user mobility. We allow data privacy using the IBC stuff. We are able to use existing internet services using proxies. We are able to use any available network. So if somebody says, I have a kiosk with Wi-Fi, a long-range Wi-Fi, and dial-up, no problem, we'll support that. And we are able to support laptop and kiosk users. So we met most of our goals, and I hope to meet the last goal by this fall. So bottom line, kiosks are a good idea. Despite all the bad press that they get in some quarters because of failures, I think they're a good idea because they're very cost effective. The cost per person is in the 50 cents to $1 range. However, the failures are because of inappropriate technology. People are taking fully featured Windows XP boxes that take 70 watts of power, they have CD-ROM drives, and they put them in an air-conditioned room with a dial-up. Okay, that's your standard, state-of-the-art today. All of these are bad. You should not be using full-feature Windows XP because it has too many viruses, worms, et cetera, et cetera. In Cambodia, people find that 60% of the network bandwidth on the dial-up is used for updating virus definition files. Okay, so this is a bad idea. They should not be taking 70 watts of power. They should be taking like a factor of order of magnitude less, like 7 watts. They should not be using a dial-up which is flaky. They should be using the buses which is just going round and round anyway. You may as well just use them. So by using appropriate technology, you can solve a real problem. And the underlying problems, when you try to build appropriate technology, are not easy. Just this graph problem I told you about is not easy. just solving the time-scale coupling problem is not easy. So this fundamental research you can do, which is intellectually challenging, but also is very applicable in this particular situation. So we think FERRIES are attractive. We have practical solutions for some of these things. Mostly working. I've told you exactly where we aren't working. And I'd like to acknowledge that the DTN code comes from Intel Research at Berkeley, and OpenDHT is also from Intel Research at Berkeley. And I have funding. This is being funded by a bunch of people, and you will note the asterisk. Thank you. Yes?
So, how would that compare to using satellite or using GPRS or normal TCP/IP?
Okay, so the question is, how about using satellite or GPRS? Satellite, you have the upfront cost of the VSAT terminal. Okay, the VSAT terminal cost, it depends on where you get it from and so on, but you're talking about roughly about $500 or so, and then you have a monthly fee to rent the space on the transponder, and that's anywhere from $50 to $200 a month. Okay, this is costing you basically nothing, right? GPRS you pay per bit, right? You pay per bit. In Canada, for GPRS service, on the lowest rate plan, I pay $23 a megabyte. Okay, and the highest rate plan, I pay $3 a megabyte. In India, it's cheaper. In India, it's about, I think it comes to about 30 cents a megabyte or something like that. But still, you cannot imagine transferring 10 pictures over GPRS. You would go bankrupt.
Like life and death certificates?
Life and death certificates, you can wait a day or two. Because right now, they have to go to district headquarters which by bus, get the certificate and come back. So it takes 2 days anyway. So you may as well just use this. So the question is, can we do low bandwidth transactional services using GPRS? Answer is yes. Okay, this is mostly useful for higher capacity value-added services like email with attachments. If you do only transactional, small kind of things, you can just use a cell phone link. Though, by the way, that's not widely available either. Okay, it's not, the coverage is not as good as you would like. So, yeah, but we're looking at essentially beyond very low-end transactions. Yeah. Yes.
We read a lot about people like Reliance trying to dig trenches around the country.
Yes.
How far are they really doing that?
Okay. The question is, people like Reliance in India are digging trenches around the country. How far is it from reality? India is, in fact, one of the most wired countries in terms of fiber. Recent studies have shown that every point in the country is within 25 kilometers of a fiber drop. Okay, a fiber pop. The fiber pops are not lit; they're dark fiber. And they were within 25 kilometers, which is quite amazing. Another statistic which actually we found quite surprising was 40% of the world's fiber is owned by India, including international fiber. So India is fiber rich. Okay. However, the issue is of can you get it to the villages from the backhaul, right? That's really what you're trying to solve over here. We're not saying we're going to have the high capacity uplink, but maybe you go from DSL to OC3, but the last mile for 100,000 villages is not easy. And that's what you're trying to solve over here. Yes?
So how does this compare to dial-up in terms of cost?
How does it compare to dial-up? Dial-up, you pay, what is it, 1 rupee a minute for dial-up? Here you pay 0 rupees a minute. It's free, right? There's a bus going round and round anyway. So other than the maintenance costs, which is, depends on outages, you're not actually doing any, there's only upfront cost. There's no monthly fees. It's just for free. Number of bytes per second. Okay, so the dial-up typically in India is 10 kilobits per second. Okay, you can get up to 5 minutes of bus time is equivalent to 1 day of dial-up. Okay, that's the ratio. Yeah. So if you have 2 buses going past, 5 minutes contact time, you're twice as fast rate of dial-up. Actually, it's faster because buses get there in a few hours. Yeah. One more question. Yes?
How many buses are you talking about total?
How many buses am I talking about?
Are they doing anything besides just this work? Are they carrying people as well?
Oh, right. So the questions are these buses dedicated to this? No, these are just regular road transport buses that happen to be going past. Well, what we do is they have 12-volt DC, We just take the 12-volt DC, put it through a power conditioner, and stick it into a soaker's box. It's just sitting there. We need to potentially drill a hole or go through a window for an external antenna, but that's it. It's an $8 antenna.
How are you handling the maintenance?
The maintenance? Maintenance of the kiosk. As I mentioned, we're working with this partner called eGov Services, and they have 80 kiosks in operation today already. The way they work is like this. They have 300 people in Delhi who are doing business process outsourcing, and they have a team that's split off to provide the infrastructure. Okay? These guys have written application front end, and they run Oracle 10G in the kiosks, and they do all the transactions and store a file, and then they train the kiosk operator to upload the file using dial-up. Okay? That's the problem right now, is that the upload is not very fast, so they can't provide email, they can't provide attachments, and they can't do very much more. What we are doing is working with these guys who already know how to run a kiosk and getting them better plumbing. Okay, that's our job. The kiosk training, the entrepreneur training, all that stuff is being handled by eGov Services, and that they plan to scale to 4,200 kiosks in about a year or so. So they are pretty well capable of doing that.
Does every kiosk have its own operator?
Yes, each kiosk has its own operator. Yeah. Okay, thank you very much.